Alrighty, this chapter deals with magnets and magnetic fields, just the very basics. We start off with the idea, of course, that magnets tend to be characterized by the idea of poles, and we said that yes, there is a relationship to Earth's north and south pole. It's not quite the one most people think, and we disentangle that as we go through. But with the idea of poles, they relate, of course, to the types of forces that magnets generate. Like poles, you should know, repel each other, force of repulsion. Unlike poles, attract each other. Now, the poles, as we see over here in figure 21.1, regardless of size and shape, magnets can be any shape, any size we want them to. And where I put the north and south pole is based on how I manufacture these magnets. What is the magnetic field they're in when they're magnetized? Regardless, they all have a north and south pole. No matter how many times a permanent magnet is cut, each piece will always have a north and south. Magnets are dipoles. Even electromagnets are dipoles. There's no such thing as a magnetic monopole. So magnetic poles always come in pairs. Now, some materials can be made into permanent magnets, and by permanent we mean that once you're magnetized, you don't have an immediate on-off switch, and I can't have a little dial right there to just change your magnetic field strength at will. Electromagnets, I can do that. Permanent magnets, I can't. If I want to make something that could be magnetic into a permanent magnet, I could stroke it or touch it to a permanent magnet. That's what we did with the lodestone and the paper clips. Or I can simply place an object near a strong permanent magnet or a strong electromagnet. That magnetic field will magnetize this new material. And if it's a strong magnetic field, it'll do it quickly. Weak magnetic field, it would take a long time. We can reverse the process either by heating and cooling or by hammering. But how easy it is to make something magnetic or remove the magnetic properties depends upon whether you're a hard or soft magnet. Know the difference between the two. When you have a soft magnetic material, they're very easily magnetized, but they're also easily demagnetized. Hard magnetic materials are difficult to magnetize. They take effort and time and money. But once they're magnetized, they tend to hold on to it extremely well. Now, magnets, of course, generate magnetic fields because the forces we see with magnets don't have to touch to have the fields, to have the forces show up. That implies that those forces are field forces. Magnetic fields, you should know the direction of magnetic field lines on a magnet always point from the north to south. And for a single magnet, yes, the field lines will loop from the north pole to the south pole of the same magnet, as easily as they would go from the north to the south pole of a different magnet. A compass, how we actually defined the direction of the field lines, was if you put a compass in a magnetic field, to which direction does the north pole of the compass needle point? Well, he would be attracted to the south pole. So the north pole of a compass needle points to the south pole of a magnet. And so in a field line, no matter where it happens to be, whichever direction is pointing towards the south, pointing along this curve, for example, going towards the south pole, that's the direction the north pole of the compass would point. So that's how we draw our field lines. Now, field lines, our magnetic field is given the variable B, so make sure you recognize that in problem solving. And you should also know that when we're working with magnetic fields, they are three-dimensional. And you need to know how to represent that as you go to analyze field lines. You should know arrow, field lines are in the plane of the page. They're running along the paper. Crosses, they're going into the page, down into your desk, down towards the floor, something like that. Right now, into your computer. Out of the page is represented by a dot. So coming up at you from your book, up at you from your test paper, out at you from your computer screen. That's used, we use a dot to represent that. Now, in this magnetic field section, they make a lot of noise about disentangling the idea of geographic north-south versus magnetic north and south. Geographic north-south is fixed. It never changes, it never varies. Magnetic does. Magnetic poles and magnetic axes actually do waffle around, so that's one difference. Two, the north end of a compass, we said, points actually towards the south end of a magnet. And that's absolutely correct. Our geographic North Pole corresponds to our magnetic south. Our geographic South Pole corresponds to magnetic north. So make sure you're very clear about what is geographic versus what is magnetic, which occurs on which end of the planet. And that they don't even line up on the same axis. The idea of true north just runs sort of up-down, like it's almost a line drawn straight up and down anywhere on the page. But magnetic north is where your compass will always point, and that's going to be different directions depending upon where you are. So for example, if we go back up to this figure 21.2, my compass needle, depending upon where it is exactly, kind of points different directions. And you need to be able to reconcile that with something like a map. And that's where the idea of magnetic declination comes in. Understand what that means and why it would be necessary to know that if you're actually using a compass to navigate. Now, moving horizontally in a compass, we kind of make them that way. We make them very flat. But in truth, Earth's magnetic field, like all magnetic fields, is three-dimensional. If you allow a compass needle to rotate freely in all directions, it'll move not only left-right, horizontally, it'll move up-down, vertically. In fact, the only place it would be completely horizontal, absolutely, positively, perfectly horizontal, is at the equator. Down here at our magnetic North Pole, if you were right dead smack on top of it, compass needle would try and point straight up, because the field lines are coming up from that point. And it would try and point straight down at our magnetic south, because the field lines are inserting straight down at that point. You should know what is the basis we feel for Earth's magnetic field. Yes, the Earth has an iron core, but it's molten. Molten materials aren't magnetic. But that molten core is in motion. There are convection currents. And that molten material is full of charged ions and electrons. Moving charged particles is the source of magnetic fields. Whether it's a permanent magnet, electromagnets, it doesn't matter. That is the source. Therefore, if that material is in motion, that would give a magnetic field, in this case, to the Earth. Don't worry about other planets, and don't worry about bacteria. Your section review questions down here, some very nice representatives. What do we see in terms of forces of attraction and repulsion for different poles? What happens if you break magnets in half, i.e. magnets are always dipoles, not monopoles? Looking at a compass and using that to tell me the direction of field lines at a location. Here, Earth's magnetic field is three-dimensional. How would a compass point if it could move vertically? And looking at hard or soft magnetic materials. They go on a lot about the idea of torque coils. Don't worry about that. That's just their example. Don't worry about torque coils. But do understand that if you have magnetic material around, if there's something else that has to remain unmagnetized, make it out of a hard magnetic material, because they're hard to magnetize. If you want it to magnetize, make it out of something soft. Now 21.2 hit the idea of electromagnetism and magnetic domains. All magnetism comes from moving electric charges, whether they're bound in a wire, bound in an atom, or freely moving, it doesn't matter. As long as the charge is in motion, there's a magnetic field. You should know for different configurations of current carrying wires, straight, looped, solenoid, electromagnet, what's going on with the shape of the field lines and the strength of the field. So for a straight current carrying wire, like down here in figure 21-6, we see concentric circles going around the wire, not through it, around the wire. The field gets weaker as we move away from the wire, and the amount of current is also relevant to the size of the magnetic field. More current, stronger field. In terms of direction of those field lines, counterclockwise or clockwise would be good descriptors, and I would use a right-hand rule to determine that. Now this I does reference conventional current, and the way I implement the rule, place my thumb in the direction of the current, grasping the wire with my fingers, or in this case might be your pencil. The direction your fingers wrap around is the direction of the field line. So in this case, my thumb upward, my fingers are wrapping counterclockwise. Also watch out for questions about, say, what would be the direction of the field lines below the wire, above the wire, etc. Look at your fingers right at that point. Which direction is the skin pointing? To the left, to the right, away from you, towards you? That could be a sort of a variation of that question. Now, if I want to make the magnetic field stronger in a wire, I could raise the current, but that could be dangerous. I could also overheat things. I can also make it into a loop. Looping the wire, not changing its length or anything else, will increase the magnetic field strength. And also it changes the properties of the field. So I'm going from concentric circles in a straight wire to a pattern here in figure A of 21-7 where it looks a lot more like that of a bar magnet. I see the field strength has intensified because my lines are very close together here in the middle of the loop. I see that it's non-uniform around the edges and weaker. I see field lines point in one direction from one side of the loop versus this direction on the underside of the loop, indicating really a north and a south orientation. So putting a single loop in a wire intensifies the field, but also makes it start to look like that of a bar magnet. Now, we still don't really have a very strong magnet at this point. The field is not really terribly strong. But if I add more loops together, each loop will actually help to amplify the overall magnetic field. And now I'm building what's called a solenoid. Solenoids produce strong magnetic fields by combining several loops together. So a typical solenoid we see on here in figure 21-8. Current running through the wires, many loops in that area. Inside the solenoid, the magnetic field is quite uniform and it's also very strong. Outside of the solenoid and along the sides, weaker field and non-uniform. I definitely have poles. I have field lines coming into this side, south, out of that side, north, and as long as the current maintains that direction, that north and south would stay in the same place. I could use this guy as a compass. Now, if I want to make the field strength even higher, I could increase the current, which again might have some dangers. I could try and squeeze more loops into this space if that's possible, and that would do it also. I can also insert an iron core and make what's called an electromagnet. Once I put that iron core in, the existing magnetic field will magnetize the iron, and he will further increase the strength of the overall magnetic field. So you should know the configuration, the shape, that type of thing, and also the strength, relatively, of a straight current carrying wire, one or two loops, a solenoid, and an electromagnet. Magnetic domains, you should be very aware of their definition. We have groups of atoms together whose magnetic fields are aligned. Normally, with electrons in an atom, take several atoms in an area, the spins all wind up with each little magnetic field that each little electron has, they cancel each other out. But in certain materials, those atoms can actually sort of align in a common direction. All the spins will kind of align commonly. And you get groups of hundreds or thousands of atoms where the spins produce a weak, but do have a net magnetic field. Each neighboring domain does not have to have the same direction of field as another. And when they don't, the material is unmagnetized. But if I place this material into a magnetic field, I'll find all these fields, all these directions of all these individual domains starting to line up in a single common direction. And that will be in line with the external magnetic field. And now that guy becomes magnetized. Demagnetize him by hitting him or heating him, and we're going to restore this very random order to the direction of the domains. I don't destroy the domains. I just bring them back to a random orientation. So when something is magnetic, like a bar magnet, all these domains point in a pretty much common direction. When it's non-magnetized, they're very random. Now, electromagnets, we don't really talk about domains because for them, when I send charges moving, they're going to move in a common direction and have common magnetic fields. And when I turn the current off, there's no magnetic properties at all. So the idea of a domain really kind of, in many cases, you might want to think of more applicable to the idea of a permanent magnet. So shapes and configurations, field strengths, etc. of different orientations or configurations of current carrying wires. The idea of magnetic domains and how it relates to things such as electron spin. Okay. And the idea of a torque rod versus a torque coil, that's just getting back to a solenoid versus an electromagnet. And then we got to magnetic forces. You should know that when you have magnetic fields interacting, you can have forces. And stationary charged particles have no magnetic field. Therefore, they do not experience any force if they're in an external magnetic field. But once they are moving, they're in motion, they will experience a magnetic force. So moving charged particles can experience magnetic forces. The force would have a maximum value when the charges move perpendicular to the field, and it basically will be zero when the charge moves along the field lines. So if I draw a line left to right, if the charge is moving left to right, it experiences no magnetic force. It moves as if it is subject to zero net force. It'll move at constant speed, constant direction. If it cuts up and down, it's moving at right angles to that particular field line, and it would have the maximum force. I don't know what the value is yet, but I know that's the highest it would get. And any angle in between is going to show an intermediate value. So, an intermediate angle, closer to perpendicular, stronger force, closer to parallel, weaker force. How do I solve for that force? I have a formula. The strength of the force is related to the size of the charge, speed of the particle, and strength of the magnetic field. Now, I do have to pay attention to whether or not this particle is positive or negative, because a positive would give me a positive force, a negative would give me a negative force, and that references direction. So in the same magnetic field, charges moving in the same direction, the forces would actually be opposite of each other in terms of direction. And we have a slide on that in class. One way to define or describe a magnetic field is by looking at the forces that a test charge would experience. Exactly the same way we kind of looked at them with electric fields. Now this formula in the yellow box and the one above it are exactly the same formula. They don't really say anything different, except this one is more focused on the size of the force a particle experiences. This is one looking at the size of a field based on the forces that a test charge is going to experience. Now force is always newtons. Charge should always be in coulomb, not micro or millicoulomb. Speed must be meter per second, and if that's the case, I do get the unit of the Tesla as my magnetic field. Now, obviously, reading problems, use units to identify material, and if there's a short answer that has you work a problem, make sure you put the right unit for the answer. Now, assessing direction, we have to use a right-hand rule. The velocity of the particle, the direction in which the particle is moving, magnetic field, and the force the particle experiences are all at right angles to each other. And using my hand with fingers, thumb, and palm, I get three things that are at right angles to each other. Now the last right-hand rule we looked at said put your thumb in the direction of the current. So it's not a big stretch to say put your thumb in the direction of the velocity of the particle. Last right-hand rule, fingers curve in the direction of the magnetic field. Put your fingers in the direction of the magnetic field. When you do so, the direction your palm is facing is the direction the force would be acting, provided we're dealing with positive charges. So whether they tell you current is running, a positive charge is moving, or they don't say anything, they just say a charge moves, that all signifies positive. You use the right-hand rule as it is here in figure 21-10 to find the direction of the force or the magnetic field lines or velocity. If it's a negative charge, you have to do a flip-flop. You can still do the right-hand rule. But for this orientation we see in figure 21-10, if this was a negative charge I was tracking, the force would be coming out of the back of my hand, be coming out of my knuckles. So make sure when you're reading a problem, is it a positive or negative? And use your right-hand rule. If it's positive, you're done. If it's not, if it's negative, you have to flip-flop your answer. Now the right-hand rule can be used to find either magnetic field direction or force direction or velocity, as long as you know the other two. And again, pay attention to positive negatives. And watch out how they describe these guys. East-west, north-south, left-right, up-down, into page, out of page. And especially for magnetic fields and even forces and velocities, you could have the convention of an arrow versus a dot versus an X. So don't let that trip you up. Problems like 21A, of course there are going to be some, solving for magnitude and direction of things. Now I said when a charge moves into a magnetic field, if it heads with the lines, parallel or anti-parallel to them, it has no net force, and it would move in a straight line. However, charges going into a field at a right angle or even at another angle are going to move in a circular path. My magnetic force is actually acting as a centripetal force. It will change the direction of the motion, but it won't change the speed. And we looked in class at how I could apply the right-hand rule at every point along this path and see the force always points to the center of the circle. My positive charge here would rotate counterclockwise. A negative charge would actually rotate counterclockwise. Different direction because it is a different charge. For a current carrying wire, my charges will experience forces and that will impact the wire as a whole. What will make a difference in the size of that force? There's your formula. Size of the external field, the size of the current in the wire, and how much wire, the length in meters, is physically present in the field. Even if some of the wire is not, you don't count him, only the part that's in the field. In terms of direction of the force, for honors, you worry about this. CP, you don't really need to. Thumb again in direction of the current, and we are following conventional current. Fingers in the direction of the magnetic field, and again, force would come out of your palm. So here we see the magnetic field lines going into the page or into your screen. We see the current going up the page or up your screen, and if you orient your fingers and your palm and your thumb just like that, you'll see your palm does point to the left. That's the direction of the magnetic force. When we're dealing, I'm snapping at my dogs because they're starting to be kind of little pains. Chris, shut up! There, now let's see if he behaves. They'll probably last about 3 seconds. As far as adjacent wires exerting forces on each other, the only thing you really need to know is just right here, A and B. When current is in the same direction in adjacent wires, forces are attracting. When the current is in opposite directions, the forces are repelling. That's it, nothing else. Loudspeakers, ignore. 21B, you do need to know how to work these problems using your formula. And for galvanometers, you should know their basic structure. I have a slug of iron surrounded by wire that would hook up to a source of current, and this whole bit is inserted into an external magnetic field. When current doesn't run, the slug of iron does not have a magnetic field, no force does he experience. When the current does run, he will experience a force that's going to torque this particular slug of iron, causing the needle to deflect. Greater the current, the greater the force, more deflection. The direction of the current determines the direction of the deflection of the needle. Ammeters, which measure currents, voltmeters, which measure potential differences, both based on the design of a galvanometer. So know how it's constructed and know what it does and know what else we can make based on its general design. Alrighty, hope that helps.